Hello class. Um, so this is video 13M, and so far we've discussed what inductive logic is meant to do, which is to give a logic of probabilities. We've discussed how to interpret the meaning of a probability. We saw the classical frequentist, the relative frequentist, and the subjectivist interpretations. And we've also looked at some important terms for understanding probability and inductive logic, like independence, fairness, bias, etc., and how understanding these terms can help us reason in everyday life, and some problems that we run into when we reason using inductive logic in everyday life, like the gambler's fallacy in our last unit. So in this portion of the inductive logic unit, what we're going to be doing is formalizing the theories of probability that we've been looking at. We're going to give equations for determining what probabilities are numerically. And these equations follow certain axioms, logical axioms, that we're not going to look at. All we're going to look at are the certain rules for determining what probabilities are and how, given certain information, we can determine what probabilities are. The rules will be basic, but take a little bit of work to understand, and that work is just using them in examples. So I'll try to make this an example-heavy section as we formalize going forward. But before we get to our equations, there are, again, some preliminaries that we need to cover before we can get to the actual mathematizing and formalizing of our inductive logic system. So our first preliminary is that events that must happen take probability of 1. So if an event must occur, like if an event is occurring right now, its probability is 1 because it is occurring. If it must be that that something will occur, it's certain, it's necessary, it could not be otherwise, then that event takes probability 1, which is like saying, and this is not a probability, this is a percentage, but it's like saying there's a 100% chance. So if there's a 100% chance of something, then that something, that event, or that occurrence takes the probability 1. And events that cannot occur take probability 0, which is akin to a 0% chance. So what we see is that events that are necessary and must occur that could not be otherwise, that will happen no matter what, take probability 1, and events that cannot occur will take probability 0. There's a 0% chance that that occurrence will happen. What's the probability that a coin flips Jack of clubs? That's an impossible scenario. The coin flips heads or tails. The probability of a coin flipping the Jack of clubs is 0. It can't occur. It won't occur. What's the probability that it rains on Mars? Well, it doesn't rain on Mars. And because it doesn't rain on Mars, it takes a probability of 0. What's the probability that in the next 10 years it will rain at least once? Well, we can probably say that that's a probability 1, that in the next 10 years somewhere on Earth it's going to rain is certain. And so we say there's a 100% chance, or a probability of 1 assigned to that event. So that's preliminary 1. Preliminary 2 is that all other events, all other probabilities occur on a scale between 0 and 1. So something that's probability 0.5 has a 50-50 chance of happening. When you flip a coin, the probability that the coin lands on heads, if it's a fair coin, is 0.5, and same for tails. And then probability 0.25, probability 0.75, right? And all of the different decimals in between. So probabilities take values that are between 0 and 1. Now, when we're doing inductive logic, when we're running our formulas, these are the kinds of answers that we should be looking for. And it's important to note that probabilities are not percentages. Percentages are their own thing. We can interpret probabilities as percentages, but probabilities themselves take values between 0 and 1. If you get an answer that says that the probability of an event occurring is greater than 1, you've gone wrong, right? Because you're saying there's a 110% chance that this will occur is nonsensical. There's a probability of 1 for certainty, a probability for positive certainty, and a probability of 0 for negative certainty that it won't happen. And every other probability will be a decimal in between those. Okay. So finally, our last preliminary is how do we write out probabilities? How do we annotate the language of probability? Well, what we do, I think in your book, the book just uses P, but for these videos, because this is how I was trained, it'll just occur more naturally for me. And feel free to use either way. It doesn't really make a difference. I use PR, and then parentheses, and then an A. So this says that the probability of A equals some number between 0 and 1, right? So we might say, what's the probability of a fair coin flipping heads on a single flip? The probability of A is our event of the coin flipping heads, equals 0.5, right? So this is how we annotate a probability. And this is the way in which we value probabilities is between 0 and 1. And with that in mind, we can begin to construct our rules of probability theory. So in this video, I'm going to be going over two different rules of probability. The first of which is the restricted conjunction rule, and the second of which is the general conjunction rule. And I'll explain what the difference is after I introduce the restricted conjunction rule. So restricted conjunction is for when outcomes are independent of one another. And if we recall from our last videos, independence is when the outcomes of games of chance or chance setups are independent of one another only if and only if they have no memory, if they're random, if there's replacement, if the occurrence of one event doesn't have a causal effect on any other event in the series of plays of that particular game of chance. So restricted conjunction is for independent events. And what we're doing is we're conjoining probabilities. So we might say, what is the probability of flipping two heads of a fair coin in a row? So flipping a coin and getting a heads, and then flipping it again and getting it heads. So in two flips, what's the probability that we get heads both times, right? And so what we're going to do is we're going to take an equation that I'll write here, which is also on page 590 in your book. I'm going to write down the equation, which is the probability of A and B now notice I used the dot, which is our deductive logic symbol for and. You could also just write the word and in here, whatever gets the point across. Equals the probability of A times probability of B. And this is our restricted conjunction rule, that anytime we want to determine the probability of two conjoined events that are independent of one another, we multiply their individual probabilities by one another. And so flipping a coin, recall, if it's a fair coin, has independence in its outcomes. Every flip is its own individual flip, and no other flip is contingent upon any other, that every flip is equally fair. And so we say the probability of getting ahead on your first flip and ahead on your second flip equals the probability of getting ahead on the first flip times the probability of getting ahead on the second flip. So what I've done is I've annotated ahead for the first flip as H1 and ahead for the second flip as H2, and now what we're going to do is we're going to multiply them together. So if we were in a class together, I would ask you, what's the probability of flipping heads on a coin? And after a moment of awkward silence, one of you would either mumble under your breath or raise your hand and say 1/2, right? That there's a 0.5 probability of flipping heads on a fair coin. So what we do is we write probability of H1 and H2 equals 1/2 times 1/2, which equals 1/4, or 0.25. So the probability of getting two heads on a fair coin in a row is 0.25. Now, we can show why this is true. And we can do it with truth tables. So this is a place where our inductive and deductive logic can help inform one another, right? That all of these tools combine and they play nicely with one another, so that as we move through the course, and hopefully you've been feeling this so far as we continue to move through the course, the tools that we're acquiring and the logical language that we're learning all begins to intertwine, right? Like we're using and symbols and annotation, whatever. So anyways, for a truth table, the probability of each of these, right? So we can think of getting H1 or H2 as our predicate variables, as just the variables that we used in deductive logic. And we know that for truth tables, with two different predicates, there's 4 possible truth values. So I write true, true, false, false, and true, false, true, false. Now, in deductive logic, we were interested in semantic meaning. That was helpful, and it was especially helpful to use the language of true and false. Now the equation is going to be the same, that the algorithm for which, so that the way in which we use our true falses, the 2, 2, and then 1, 1, 1, 1, right, the alternating, is going to be the same, but rather than talk about truth, we're going to be talking about head flips. So for coin 1, we will have a heads, a tails, and then for H2, we'll have heads, tails, tails. Right? This is all of the different possible combinations of 2 different coin flips together. Either you get a tails on your first flip and a tails on the second flip, or you get a tails on the first flip, a heads on the second flip, you get a heads on the first flip, a tails on the second flip, or a heads on the first flip and a heads on the second flip. Now, what we're looking for is the probability of getting the heads on the first flip and the heads on the second flip. We can see in our truth table that there's one line where that occurs in the first line, and in no other scenario does it occur. And so 1 out of 4 times we get 2 heads in a row, and so our probability is 1/4 or 0.25, right? And so this is just sort of a helpful exercise to see how truth tables can help us to prove or justify or even just reaffirm our probability calculus. Okay. So the restricted conjunction rule is for when events are independent. What if we want to find out the probability of events that are dependent, that are not independent, but conjoined? So for instance, if I asked, what is the probability of drawing 2 jacks from a deck of cards? Now, there's 4 jacks, and the probability of pulling 1 jack is 4/52, right? Because there's 4 of them and 52 cards. So taking the frequency, we can tell that there's 4/52 probability that I pull 1 jack. But once I pull that first jack, the game changes. There's no longer 52 cards and there's no longer 4 jacks, so our probability changes. The events are not independent of one another. And because they're not independent, we're not going to be able to calculate the probability of pulling 2 jacks because the game changes. The probabilities are affected. And so we need a different rule, and we call this the general conjunction rule. And the reason we call it general is because the general conjunction rule will apply to any conjunction of probabilities, all whether independent or dependent, whereas the restricted conjunction rule only applies to independent outcomes when conjoined together. So what that means is that basically you can use the general conjunction rule in every case. If you wanted to be safe, you just always use the general conjunction rule as opposed to the restricted conjunction rule, but it's slightly more complex. It requires one extra mental calculation. So let's write down that equation. Okay, so you'll notice that it's very similar, but a little bit different. So the probability of A and B here is just the probability of A times the probability of B. But as we noted with the drawing 2 jacks from a deck of cards, our first scenario is drawing a jack, but our second scenario, the probabilities change because the deck changes, the game changes, and we need an equation to account for that. So the way that we recognize this in notation is we write the probability of B given A's already having occurred. So this B's occurring, or B, the probability of B given A's already having occurred is our way of saying that the probability that we're calculating is the probability based in the new game, in the new deck of cards. And this will look very much similar. So the probability of A and B, and let's use the drawing 2 jacks in a row from a deck of cards, equals, well, what's the probability of drawing 1 jack? And again, after some amount of time and awkward silence, one of you might mumble, well, it's 4/52. And I would say, correct, good. So the probability of pulling a single jack from a full deck of cards is 4/52. But as soon as we've drawn that jack, the amount of cards reduces down from 52 to 51, and the amount of jacks in the deck reduces from 4 to 3. So to draw a jack from that new set would change what our probability is. The probability of B given A, given that this has occurred, is 3/51. And that's because as soon as A has occurred, there's only 51 cards left in the deck, and only 3 of those, because one of them was pulled, is a jack. Now, there are ways to calculate the B given A mathematically. It's called conditional probability. We're not going to go through the rules of conditional probability in this class. We'll save that for 3210, which is the more advanced inductive class if you get interested. There is a way to calculate that mathematically. For this class, all of our examples and on your quizzes and tests and everything will be easy enough to just know, like this, that once a card has been removed, the game changes from 3 to 51 or something like that. We'll be very clear about it, or alternatively, we'll just give you that value. So the probability of B given A, when A occurs, reduces, the deck size to 51 and the amount of jacks in it to 3 over 51. And all of a sudden, we see that we see why we can't apply the restricted conjunction rule, because the restricted conjunction rule would just have the probability of A and the probability of B, both of which are drawing jacks, as 4 over 52. But because the outcomes are dependent, or the outcome of B is dependent upon the outcome of A, the outcome of drawing a second jack is dependent upon the outcome of drawing a first jack, then we need a different probability value here. And it turns out that this equals 1 over 221. So one time out of 221 times, you will draw 2 jacks in a row from a deck of cards. So the PR of A and B, where A and B are not independent, and these are our probability calculuses for probability of A, and B given A is 1 over 221. And that concludes our first lecture on the initial rules of probability calculus. For the next one, we're going to do something very similar. We're going to be talking about rules of disjunction. So in this lecture, what we talked about was how to combine probabilities together, say what's the probability of getting both of these events. In the next lecture, we're going to ask how do we determine the probability of getting either of these events. And that will be in video 14M.